Okay, we're going to continue with a couple of examples to show the applications of compound angle identities. We are supposed to find cosine of 15-degree angle. Of course, 15-degree angle is not a special angle. In trigonometry, special angles are 30 degrees, 45 degrees, and 60 degrees. And we know by heart, actually, what the exact values of trig ratios of those special angles are. For example, sine of 30 degrees is 1/2, but sine of 60 degrees is square root of 3/2. Or cosine of 45 degrees is actually square root of 2/2. Some calculators nowadays, when you press the button, of course, they give you the exact value. But some other models of calculators, they only give you the decimal values. But anyhow, we want to find the exact value of cosine of 15 degrees. That is the question. How can you find the exact value of cosine of 15 degrees? So what we're going to do, we are going to think of 15 degrees as the difference between two angles. So let 45 minus 30 equal to 15 degrees. So instead of 15, we can write it as cosine of 45 degrees minus 30 degrees. We can break it down basically, okay? And then we can use the subtraction formula for cosine, or one of the compound angle identities we have proved in the past. Cos of alpha minus beta is cos alpha cos beta plus sine alpha sine beta. So here I can say it's cos of 45 degrees times cosine of 30 degrees plus sine of 45 times sine of 30 degrees using the compound angle identity. So this would be root 2/2. Cosine of 30 is root 3/2, and sine of 45 root 2/2, and sine of 30 is 1/2. It is our duty to know the exact values of trig ratios of special angles. So that's why you have to write this fluently. Now, root 2 times root 3 is clearly root 6/4, and we have root 2/4, same denominator. Therefore, root 6 minus root 2/4 would be the exact value of cosine of 15-degree angle. So we did find the exact value of cosine of 15-degree angle. If you evaluate this fraction using the calculator, press the square button, you will see that it is exactly the same number as cosine of 15 degrees when you press the cosine button on your calculator. This next example is tangent of pi/12. This time it's not in degrees, it is in radian. I think you already know, most likely, pi, like 5 pi/12 radian is actually 75 degrees. And when you think about it, 75 degrees can be broken down as 45 degrees plus 45 degrees plus 30 degrees, I guess, right? So it would be tangent of pi/4, which is 45 degrees, plus pi/6, which is 30 degrees. So 45 degrees plus 30 degrees is 75 degrees. So basically, we are breaking down 5 pi/12 radian as the sum of pi/4 radian and pi/6 radian. So we remember we had the formula of tan of alpha minus beta. It was the tangent of alpha minus tan of beta, 1 plus tan alpha tan beta. Now, if instead of negative beta here, if instead of having alpha minus beta, if you have like a negative angle sitting instead of beta itself, then you end up with tan of alpha plus beta, because that new angle, negative beta, if you plug in, it becomes alpha minus that negative beta, which is alpha plus beta. So if you plug in negative beta instead of beta in the left-hand side, you should do the same thing on the right-hand side. So that tangent of beta on the right side becomes tangent of negative beta, which is negative tan of beta, according to negative angle identities we have studied in the past. Same thing in the bottom. So the formula becomes tan of alpha plus tan of beta over 1 minus tan alpha, tan of beta. So that is the addition formula for tangent, which I quickly derived from the subtraction formula for tangent. Even for cos of alpha minus beta, now I know we are in the middle of something else, but even for cos of alpha plus beta, you can do the same thing. You can say cos of alpha plus beta is cos alpha cos beta, and then minus sine alpha sine beta. So these identities can easily be derived from one another. Or for the sine, sine of alpha minus beta was sine alpha cos beta minus cos alpha sine beta. But then if you want to find sine of, let me write this neatly. Okay, so sine of alpha plus beta would be sine alpha cos beta plus cos alpha sine of beta. So addition subtraction formula for sine, addition subtraction formulas for tangent, and for cosine. So making a long story short, we break down 5 pi over 12 radian into pi over 4 radian and pi over 6 radian, the sum. And then we're going to apply this identity. We're going to say this is tan of pi over 4 plus tan of pi over 6, because tan alpha plus tan beta, minus tan of pi over 4 times 1 minus tan of pi over 4 times tan of pi over 6. So everyone knows tan of pi over 4, tangent of 45 degree angle is 1. So plus root 3 over 3, 1 minus, again, root 3 over 3, which is tangent of pi over 6. So in the numerator, if you find the common denominator, you get 3 plus root 3, let's say all over 3, and then that is over 3 minus root 3, again over 3. If you simplify, you get 3 plus root 3 over 3 minus root 3, because 3 and 3 cancel out each other. Now the thing is that this is the right answer, this is an exact value, but we want to rationalize the denominator. So what we do, we're going to multiply this by the conjugate radical of the denominator in order to rationalize the denominator. So we get 3 plus root 3 all squared, and the bottom is actually the difference of squares. If you think about it, a minus b times a plus b is a squared minus b squared. So which is like 3 squared minus square root of 3 squared. So that would be 9 minus 3. Okay. And that gives you 6. Now in the numerator, we have a plus b all squared. Perfect squares identity. Or we can just sit down and expand and multiply the two binomials. So we get 9 plus 3 plus 2 times 3 times root 3. I'm using perfect squares identity. So 9, 10, 11, 12. So that's 12 plus 6 root 3 over 6. Then I'm going to split this 12 over 6 plus 6 over 6. And eventually I get the answer, which is 2 plus root 3. Therefore, the exact value of tangent of 5 pi over 12 radian is equal to 2 plus square root of 3, which is roughly 3.7 if you punch it on the calculator. Okay, so by these two examples, I just wanted to show you the applications of the compound angle identities. One of the applications, mind you, but we can use these identities to prove other identities, which we will do it in future. I just wanted to show you an immediate application of compound angle identities for now. Thank you.